Değerli katılımcılar, hepiniz bugünkü webinarımıza hoş geldiniz. Öncelikle tahmin ediyorum hepiniz Sayın Volkan Boza'yı bekliyordunuz ama küçük bir değişiklik oldu. Bugünkü webinarın moderasyonunu ben gerçekleştireceğim. Çimento üretiminde ve kullanımında emisyon azaltımı fırsatları konuları webinarımıza tekrardan hepiniz hoş geldiniz. Hepinizin bildiği üzere 2050 ve 2053 hedeflerinde üstümüze düşen görevleri yerine getirebilmek adına farklı konularda webinarlar düzenledik geçen yıldan bu yana. Bugün de Norveç'teki yapılan çalışmalar ve uygulamalarla ilgili olarak sizlere bir sunum gerçekleştirilecek. Bu konuda sunumu gerçekleştirecek olan Doktor Sunari Kvendorp'u size tanıtmak istiyorum. Kendisi Oslo Üniversitesi'nde ekonomi alanında doktora derecesini tamamlamıştır. Daha sonrasında şu an halihazırda da Frisch Center'da kıdemli araştırmacı olarak görev almaktadır. Aynı zamanda Mr. Kvendorp son 4 hükümetler arası iklim değişikliği paneli olan IPCC'de değerlendirme raporlarında yer almış ve bu raporlara katkı sağlamıştır. Ayrıca bu Mr. Kvendorp'la tanışmamızı sağlayan Doçent Doktor Tunç Durmaz'a da ayrıyeten teşekkürler etmek isterim burada sizlerin nezdinde. Bu tanıştırma ve bugünkü sunuma vesile olduğu için kendisine çok teşekkür ederiz. Mr. Kvendorp'a ben sözü bırakıyorum. Sadece sizlerden bir istirhamım olacak. Sunum sırasında, webinar sırasında sorularınız olursa soru cevap kısmına yazarsanız sunum sonrasında da bu soruları Mr. Kvendorp'a yönlendirebiliriz. Mr. Kvendorp, söz sizin. Buyurun.
Thank you. And thank you for inviting me to this presentation. I'm very honored to be invited to this. Let me share my presentation. So I'm going to talk about opportunities for emission reductions in the production and use of cement. So this is based on a paper I co-authored with Oskar Vågerø and Erik Nevdal. Unfortunately, this paper is written in Norwegian, but I'm going to go through the paper and give you the main conclusions from this paper. The reason why we started to work on emission reductions in cement production and use is that about 2 years ago, the Norwegian government decided to support financially a demonstration plant for carbon capture and storage, which we call CCS, at one of 2 cement factories in Norway. We have actually 2 cement factories in Norway, and this is one in the north of the country and one in the south of the country. And the biggest one is in the south of the country in a place called Brevik. So this is supposed to be the first cement factory with CCS, with carbon capture and storage in the world. So why cement? So why did actually the Norwegian government choose to use cement as a kind of demonstration plant? Well, the reason for that is that cement is the industry sector with the highest greenhouse gas emissions in the world. For instance, it's supposed to contribute to about 6 to 8% of global CO2 emissions. Also, cement is usually called a sector which is hard to abate. It's hard to abate in this sector. And the reason for this is actually process emissions, which I'm turning to now. So where do emissions from cement production come from? So if we stick to the ordinary Portland cement, which is the common cement produced, clinker production in Norway contributes to about 2/3 of emissions from cement production. And the heating process contributes to about 1/3. I've seen some global numbers, which is about 60% for clinker production and 40% from heating. But this depends a lot of what kind of fuel you use in the heating. So if you want to reduce emissions from production of cement, there are 2 ways of doing that. One is to reduce emissions from process, and one is to reduce emissions from heating. If we consider process emissions, we could consider clinker substitution or producing alternative types of cement, which means other processes. If we consider heating, emissions can be reduced by energy efficiency or use other types of fuel with a smaller carbon contents in the heating process. So I'm going to go through both of these two ways, or actually 4 ways then, to reduce emissions from production. But on the other hand, it's also possible to reduce demand for cement, which will also reduce emissions from cement. In the EU, for instance, cement is used for buildings, 50%, infrastructure, about 30%, and maintenance, about 20%. So, and cement is mainly used as a binder in concrete. So if we want to reduce cement production in the way that we want to reduce demand, we could reduce the use of cement in concrete, meaning kind of substitute cement with other products in concrete, or we could use alternatives to concrete, wood or whatever it is, some alternatives to concrete. This would reduce the demand for cement and also reduce emissions. So what I'm going to do in my presentation, I'm going to go through both ways of reducing emissions from production and ways of reducing emissions from demand for cement. And I'm going to see what this may have, how much emission potential for reducing emissions based on this. I'm mainly going to use figures for Norway, as this was based on the cement factory in Norway. But I also use figures which we take from the research literature, so the figures I'm going to use may not be necessarily representative for Turkish cement industry. So let's start with cement production, and let's start with emission reductions from heating. One way of reducing emissions from heating is actually to have an increased energy efficiency. According to the research literature, there's a relatively small potential of reducing emissions from energy efficiency. About 3% is actually the potential that is mentioned in the international research literature. On the other hand, energy efficiency has quite very low cost actually. You may need to do some additional investments, but the payback time of these investments may be small compared to the costs of reducing fuel. So it's reasonable to assume that energy efficiency has a very low cost or actually a 0 cost in the long run. Another way to reduce emissions is alternative fuels for heating. In the cement factory in Norway, Brevik, it uses waste. 42% of the fuels for heating is waste, 30% is biofuels, and 28% is fossil fuels. But this varies from cement factory to cement factory. So in principle, it is possible to only use biofuels and reduce emissions by 1/3, as in Norway, 1/3 of emissions come from heating. There may be several limits to that, but in principle, it's possible to do that, especially probably in Northern Europe, where we have more forests we can use for biofuels. According to a study actually 2 studies by McKinsey, this would mean higher costs. So if you translate these costs to cost per ton CO2 that we actually emit, so this may mean something like 6 to 14 euro per ton CO2. So these costs actually reflects what we call marginal costs of abatement. So this means how much does it cost to reduce 1 ton of CO2. So all the costs I'm going to refer to now are marginal costs of abatement, the cost of reducing emissions by 1 ton of CO2. So by using biofuels, according to this McKinsey study, the cost would be between 6 and 14 ton per 6 and 14 euro per ton CO2 we reduce. So in what I'm going to show you, I'm going to use the highest number here. I'm going to use 14 euro per ton CO2. Another way is to reduce clinker, to substitute clinker in cement production. There exist several materials that can substitute clinker. They are usually named supplementary cementite materials. Some of these materials are relatively cheap, but they are limited in supply. Some example of this could be granulated blast furnace slag from steel production, GBFS, or fly ash, which is a residual product from coal-fired power plants. But these substitutes are kind of limited in supply. So if you look at substitutes that are not so limited in supply, one alternative could be calcinated clays. But this would require investment in a calcination factory. According to international research literature, it could be possible to reduce the share of clinkers or to substitute the share of clinkers by as much as 50%. So this would mean actually emission reductions by 1/3 based on these Norwegian numbers. There could be arguments against this, that this would have impacts on the quality of the cement produced, but I think that the literature is not very clear on this. So this may reduce costs. I say may reduce costs because if you have an investment in a calcination factory, this may actually mean higher costs. But I haven't really been able to find some good numbers from literature on this. We found one study from Cuba saying that the costs of producing cement could increase by something like 30–35% if we substitute clinker by calcinated clay. So, but what we're going to do now, we're going to set marginal cost equal to 0, which is basically if we use very cheap alternatives. But this may actually be too small. It may actually be higher than this. So if we look at alternative types of cement, also as a way of reducing process emissions, there are two alternatives that are mentioned in the literature. One is called RBPC clinker, which can be produced in conventional cement factories without large changes in the process. So this type of clinker is, for instance, used in the world's largest hydropower plant in China called Three Gorges Dam. And this may reduce emissions by about 10%. The cost of using this is similar to the ordinary Portland cement, so that means we have no extra costs of using this. According to Norcem, the Norwegian cement factory, it says that it's not so suitable for slim constructions in cold climate, but I'm not sure. So maybe it's more suitable in Turkey, which has a warmer climate. I don't know. But could be some restrictions to the use of RBPC clinker as well. Another type of clinker is called BYF clinker. This may give 28% lower emissions, but increase costs. But this clinker type is not yet approved under European standards and therefore not produced commercially. So the last alternative I'm going to mention is CCS, carbon capture and storage, which was actually the main reason why we started to look into this. So the plant, which is under construction in Brevik, Norway, is a post-combustion plant. Post-combustion means that CO2 is captured after the combustion. This plant is part of the Norwegian Longship project. The Longship project is actually a project for capture, transport, and storage of CO2, and it covers the cement factory in Brevik, and it also covers waste-to-energy plant in Oslo, which is supposed to be built as well, but the funding is not yet finished, but it's probably going to be built very soon as well, the waste-to-energy plant in Oslo. So this plant in cement factory in Norway will capture about 50% of emissions. It is technically possible to capture much more than this, like something like 90% of emissions. But the reason why the cement factory in Norway decided to only capture about 50% of emissions is that it can utilize all the waste heat that has very low alternative cost or zero alternative costs. So if you want to increase the capture by more than 50%, up to 90%, the cost would be much higher. We were not actually able to find exact costs for CCS in this cement factory. So in our study, we use the cost from Çimento, which is also a cement factory owned by Heidelberg Group. Norcem is cement owned by Heidelberg Group, which is in Sweden, which also plans a CCS factory in Sweden from the cement factory at Gotland in Sweden. And according to this will cost something like 94 euro per CO2 reduced. But this is without transportation and storage. This is only capture, so the cost would be higher. I'm not exactly sure how much higher it will be, but something maybe 120, 130 euro per CO2 reduced. So it's quite high costs actually. So if you look at the measures I've been talking about so far in cement production, we have several combinations. In combination one, where we actually assume that the factory is going to continue to produce ordinary Portland cement, we have energy efficiency as a way to reduce, we have clinker substitution, and biofuels. If we study combination two, where we use RBPC clinker, we have energy efficiency, we can have RBC clinker instead of OPC clinker, and also biofuels. So what we assume now is that clinker substitution is not possible for RBPC clinker. That may not be true, but at least we didn't find the possibility when we looked at the literature. So we only use clinker substitution for OPC. If clinker substitution is possible with RBPC clinker as well, the potential for emission reductions will be much higher. So this figure is actually measuring the costs for clinker substitution, for emission reductions from production. So this is combination one, which is where we actually continue to produce OPC, ordinary Portland cement. And on the x-axis, this can you see when I point? Can you see when I point here? Yeah, okay. So here we actually measure the cumulative emissions of CO2. And this is actually marginal cost of emission reductions in Norwegian kroner. This line up here is the cost of CCS. The dotted line used to be the ETS price in Europe. When we draw this, it was the average price for the last 2 years was about 25 euro per ton CO2. But today it's actually much higher, it's about 80%. So it'd be something up here, the ETS price. But anyway, what this shows is actually that by using combination one, that means using energy efficiency, clinker substitution, and biofuels, it is possible to reduce emissions from from cement production by something as much as 50%, and maybe a little bit more. If we use RBPC clinker, we can reduce emissions by something like about 35%. And these emission reductions would be lower than, to a cost lower than the ETS price in Europe, and also lower than the CCS costs. But what this also shows that it's not possible in cement production to reduce emissions down to zero without the use of CCS. So it's very hard to reduce emissions down to zero, which will be necessary in the long run, according to the latest IPCC report, if we don't use carbon capture and storage. On the other hand, it's also possible to reduce the demand for cement. And I'm going to consider two ways of doing this. One is called cement efficiency, which means replacing clinker with other material. Replacing cement with other material. So concrete consists of about 7 to 20% of cement. According to international literature, research literature, about 70% of cement can be replaced by, for instance, limestone without reducing the mechanical strength of cement. This can reduce emissions by about 50%. and the costs will probably be reduced as well. There are some objections to this. For instance, some people claim that the quality of cement may not be the same by reducing cement by something like 70%, but at least according to this literature, the mechanical strength will be about the same. So this is called cement efficiency, reducing cement in concrete. So what about something concrete efficiency? Concrete efficiency here means that we can use simpler construction, use less cement, less concrete, and also recycling of concrete. According to the literature, it's usual to have a better safe than sorry principle, in the construction business. So that means that maybe they use a bit too much cement in different building constructions or infrastructure constructions. So according to one study, cement can be reduced as much as 20% in the different constructions, and this will therefore not add to costs. So it's possible to reduce cement both in concrete and also reduce concrete in demand. So what about if we substitute concrete for other materials in constructions? One option could be to reduce wood instead of cement. And wood is more widely used now than it used to be several years ago, for instance, in buildings. And the world's tallest wooden house is actually in Norway. It's about 85 meters tall. But it's really hard from the literature to estimate the effect on emissions and the effects on costs of doing this. So I haven't actually used any numbers for this, but this could be an alternative. Two other types of cement, which is not yet produced, they are really immature, but maybe there can be a possibility in the future, in a couple of decades, for instance, is biocement and mycelium. But these are not options today, but they may be possibilities maybe in the future. So let's now take a look at the different possibilities, both on the production side, as we already talked about, and the demand side. So I look at two combinations. One is if we continue to use ordinary Portland cement, and the other one if we use the RBPC clinker. So if we use combination 3, Portland cement, we have energy efficiency, clinker substitution, and cement efficiency, energy efficiency, clinker substitution, and biofuels as before. And we also add cement efficiency and concrete efficiency on the demand side. Also, if we use RBPC, we have energy efficiency, RBPC clinker, and biofuels as before, and we add cement efficiency and concrete efficiency on the demand side. So looking at this graph, this combines the possibilities on the demand side and production side. And as you see from this figure, if we use combination 3, which is to continue to use ordinary Portland cement, ordinary Portland clinker, we can actually reduce emissions by as much as more than 80% without using CCS. So this is energy efficiency, clinker substitution, cement efficiency, concrete efficiency, and biofuels. And you see that this is actually possible to do to a very low cost. In this figure, we actually have cost equal to 0. But this is possible to do with a very low cost, a cost which is actually lower than the ETS price in Europe, and which is this line, should be a bit higher, and also compared to CCS. If we use RBPC clinker, we also can have a quite high potential here. Up to almost 80% can be reduced on the demand by having actually measures on both the production side and the demand side. So what have we shown by this study? Well, we show that it's theoretically possible to reduce CO2 emissions from production with about 50% without the use of CCS, while additional measures on the demand side may reduce emissions with more than 80%. So this is based on the numbers we have from Norway, and it's also based on numbers from the international research literature. But this does not necessarily reflect possibilities everywhere. It depends on the plant, it depends on the country, it depends on climate. So this number I've shown here does not necessarily reflect the possibilities in Turkey. But on the other hand, we show at least some of the possibilities that can be used. And Norcem actually plans to use several of the measures studied in this study. And the aim of, or the goal of Norcem is actually to be carbon neutral by 2030. It doesn't mean that the emission is going to be zero, but it means that they're going to use a lot of CCS combined with some of these measures, and probably going to buy emission permits in the EU of the rest of the emissions. But there are several restrictions to what I've also shown you already. I mentioned some of these. So clinker substitution and cement efficiency may affect water requirements, castability and durability properties of the concrete. So this may actually be one disadvantage. So this may actually reduce the quality of the concrete. There are also different standards, usually one European standard and one North American standard. And according to Norcem, the maximum permitted admixture of a calcinetic clay as a way to substitute clinker is 35%. But we have assumed 50%, which is assumed in some of the international literature. And one thing I showed you that the costs are going to be small, but these costs do not necessarily cover all costs, because there may be changes in routines, we may change education, maybe changes in logistic systems, etc., etc. That may actually give higher costs, but these costs are not necessarily very easy to estimate. So there may be actually costs that are not included in these estimates, but that may actually increase costs. So one conclusion may be to educate, for instance, architects, building engineers, and so on, so they actually can be able to use some of these measures that we show here. So one thing we can discuss also, because EU is planning to introduce carbon toll for cement. So not only for cement, but for imports that are not covered by the ETS system. So what can we say about this? Well, one thing, if you look at the market share of cement in different countries and how much is exported, the market share of Norcem in Norway is 75%. So Norcem actually covers most of the whole market in Norway. And the rest is imported from Germany, Denmark, Sweden, and the Netherlands. So the weight and value of cement makes it less attractive as an internationally traded good. I think about 15% of the cement produced in Norway is exported. And I was trying to look up numbers for Turkey. So correct me if I'm wrong, but I think it's about the same in Turkey, about 15% totally exported from Turkey. So cement is not so attractive as an internationally traded good. So what about if we double the production costs of cement, for instance, double by using carbon capture and storage? This will increase the cost of final product. So I found some numbers from Norcem. So according to the Norwegian numbers, if we double the production costs of cement, it will increase the price of buildings by 1 to 2%, infrastructure of 4 to 8%, and cement products by 25%. I just looked at the web page for the Turkish Association, Cement Association, and I think you have higher numbers on your web page. And this may reflect, for instance, that labor costs are higher in Norway than in Turkey. But anyway, so doubling the production cost of cement will not affect the price of the final product very much. So one conclusion from this is cement is probably not very price sensitive in demand. So demand for cement is probably not very price elastic. That could be one conclusion. And if you look at the border carbon adjustment mechanism, the CBAM, this is a tax on consumption in the EU rather than production. And if consumption is not very price sensitive, one way of thinking about this is that it may probably not change consumption so much. But I haven't really studied this, but this is some preliminary thoughts I have about the effects of increasing cement price due to measures to reduce emissions, that it may not be very price sensitive in Europe. So let me end my presentation by saying a few words about CCS. So one conclusion I mentioned to you already is that it is not possible to get to zero emissions in cement production today without the use of CCS. And this is also the conclusion of IPCC, the report that was launched recently, a couple of weeks ago. But this may change within a few decades if we come up with better types of cement, which is much more low in carbon content. If you look at carbon capture and storage in Norway, so the Norwegian goal is to reduce emissions by 55% in 2030 compared to the 1990 level without the use of EU ETS, that means buying permits in the European markets. And CCS will contribute to the realization of Northern Lights. Northern Lights is actually the name of the transportation and storage system in the North Sea. So this will also cover, in addition to the cement factory, this waste to energy factory in Oslo, as I mentioned, which also plans to have CCS, and hopefully also other CCS projects around the North Sea. So there are many plans for carbon capture storage around the North Sea, and there may be competition for storage sites. So I just want to show you a map of the North Sea. You have Norway up here, and the North Sea is divided into several economic sectors. So this is the Norwegian sector, the British sector, Dutch, German, Danish sector. The cement plant in Norway is around here, where I show you with this arrow. The plan is to transport the carbon, going to cool it down, transport it by ships around the coast up to a terminal, which is around here. Oh, sorry. A terminal, which is around here, and transport the CO2 with pipes out to a storage place in the North Sea. So several other countries around the North Sea, Denmark at least, Netherlands, and the UK, they also plan CCS in industry. So there may be a competition for storage sites in the North Sea. The Norwegian project, which is called Northern Lights, hope to get a lot of customers from other countries as well. And Sweden, which is out here somewhere, they also plan a CCS at their cement factory in Gotland. So Northern Lights project hopefully gets Sweden as one of their customers. So cement is actually only one of several factories which is going to use CCS within a few years' time in the North Sea to store the CO2 offshore in the North Sea. Okay, so let me finish my presentation. So one thing I recommend you to read is chapter 11, which is about industry in the latest IPCC report on solutions on mitigation, which was launched about 2 weeks ago. So this is available if you go to the webpage, ipcc.ch. So there, this chapter is actually also saying something about possibilities for cement. I also added to the end of my presentation some references to some of the literature I refer to, which is in English. So if you're interested, I sent this already, and I can send my updated version because I changed a few things yesterday. So here's also some literature that you can look at if you're interested. Okay, thank you.
Sayın Kıvendor, çok teşekkür ederiz. Senin çok faydalı bir bilgilendirme ve açıklayıcı oldu. Sorular kısmına baktığımda bir tane soru var ama eğer Kadir Bey müsaade ederse ben birkaç tane soru sormak istiyorum. Onun öncesinde eğer cevaplayabilirse Kıvandor çok teşekkür ederim. Bu yapılan çalışmada şundan bahsettiniz. Biz de hani bu konu üzerine çünkü ciddi anlamda hani fikir birliği ve kafa yoruyoruz bu konuda. Yüksek fırıncı rüfu uçucu külün hani klinker ikamesi olarak kullanımı konusunda. Bu çalışmada karbon ayak izlerine bakıldı mı acaba? Yani bu malzemeler kullanılırsa karbonun yüzde kaç azalacağına dair bir çalışma var mı acaba? Onu soracağım ilk önce. Biliyor musunuz? Hani?
Yes, let me see if I can find the slide here. Yes. So the point is, if we use clinker instead of producing, sorry, if you use, for instance, fly ash instead of producing clinker, we can actually get rid of the emissions, parts of the emissions from clinker substitution. So one study says that the share of clinker can be reduced by 50%. So this is based on this paper I have on the end of my slide. So if you look at 50% reduction of something like 2/3 of the emissions, if you say that 2/3 of the emissions come from production, from the process, then we can reduce emissions by 33%. So this is based on this study. So this is one way of doing this. It is a discussion if it's possible to reuse by as much as 50%. As I mentioned, some may claim that it may affect the quality of cement, but this is at least based on this study. So I think I would recommend this paper actually. It's at the end of my presentation. I think probably it will be available to you, my presentation, so you can look at that reference. So according to this, clinker substitution by using like fly ash or other ways can actually have a large effect on reducing emissions from the process.
Teşekkürler. Bir diğer sorum da Norsem'de karbon yakalama konusu üzerine hani yatırım olduğundan bahsettiniz. Buradaki yatırım maliyetleri ve işletim maliyetleriyle ilgili o bilginiz var mı acaba? İşletme. CAPEX, OPEX.
I don't think I have the total costs here, but it's possible to. So what I actually looked at now was actually just, let me see. I just looked at the costs when we actually calculate the costs per unit of emissions reduced. So this is actually the cost per, that actually would mean per unit of emissions produced only from capture. So it will cost €94 to reduce emissions of CO2 with 1 ton. I don't have the total costs available now, but it is possible if you look at the web page for the Northern Lights project. I think I have also the references behind here, but it is very costly. And it requires some financial support from the government to be able to do this. So why the Norwegian government uses this is that I think actually it may be possible to these kind of demonstration projects, so the costs will fall in the end. So somebody has to be kind of a leader in the market, and then costs will fall in the end. So it's probably going to be learning effects and R&D effects as well. So it's going to be cheaper in the end. But it's not worthwhile for industry to do this alone. It needs some support by the Norwegian government. Norway is a richer country than Turkey, and Norwegian government decided to do this. And also it sees this as a kind of business opportunity when it comes to storage sites in the North Sea, because CO2 can be stored in empty oil and gas wells in North Sea. And some of this is already used. We have, for instance, been storing CO2 in the North Sea since 1995 from actually the oil platforms in the North Sea, because we introduced a CO2 tax already in, I think it was about 30 years ago. And this CO2 tax meant that it was more, it's better for the industry to actually to store the CO2 because some of the natural gas they sell has a high content of CO2. So they need to take out some of the CO2 from the natural gas. And it was better for the businesses or for the oil industry to remove that and store it in the North Sea than to pay the carbon tax. So CO2 has been stored in the North Sea since 1995, and they have very good experience with that. And so far, we have no leakage in storing CO2 in these empty oil and gas wells. So I think the Norwegian government sees this as a business opportunity as well, and hope to attract a lot of customers from other countries around the North Sea, and also like Sweden, for instance. So it could be actually a business opportunity, even if it's expensive.
Norveç dediğiniz gibi hani yani coğrafi lokasyon olarak hani depolama konusunda çok şanslı bir ülke. Ama Türkiye tarafına baktığımız zaman Türkiye'nin bu kadar depolama sahası, hani Türkiye'deki karbondioksit emisyon miktarı düşünürse o kadar yeteri kadar bir depolama sahası yer almıyor. Sizde gördüğüm kadarıyla zaten sadece depolama üzerine yoğunlaşmış durumdasınız. Yani karbonu yakaladıktan sonra bunu yeniden kullanım üzerine bir şu an çalışma yok anladığım kadarıyla. Fakat bizler Türkiye olarak yani karbondioksiti yakalama ve bunu yeniden kullanımı üzerine çaba sarf etmemiz gerekecek diye düşünüyorum ben. Norveç'te Türkiye'ye kıyasladığım zaman hani baktığımda, coğrafi olarak hani baktığımda o sanırım bizim dediğiniz gibi hani bu şu an bizler de şey olarak hani maliyetlerin çok yüksek olduğunu biliyoruz. İlk yatırım maliyetlerini, daha sonrasında da işletme maliyetleri. Hani o yüzden siz bu çalışmada rakamsal bir şey biliyor musunuz? Toplam karbon yakalama ne diyelim sisteminin hani ne kadar mal olduğu ve daha sonrasında bunu işletmek için diye özellikle sormak istemiştim ama sizde de anladığım kadarıyla toplam rakam mevcut değil. Şimdi soru cevap kısmına geldiğimizde ben Türkçe mi sorayım, İngilizce okur mu kendisi? Soru İngilizce olarak sorulmuş Kadir Bey tarafından. Yani Norveç'te jeopolimerlerle ilgili olarak hani beton anlamında durumun ne olduğunu ve endüstriyel olarak hani ready mix dedikleri yani hazır betonda jeopolimer beton üretimi var mıdır onu soruyorlar. Yani bilgisi var mıdır acaba? Norveç'te böyle bir şey var mı?
Could you repeat the question in Norway?
Tamam, teşekkürler.
No, I know. Not as far as I know. It's not as far as I know. But I may be wrong. But I haven't heard about that.
Tamam, teşekkürler. Bir diğer soru Yasin Bey tarafından hani gelmiş. Bizim kullanmış olduğumuz çimento ve beton standartları var. 197.1 ve 206 standartları. Bu standartlar içerisinde kullanılacak katkı miktarları ve katkılarla ilgili olarak hani miktarlar belli bir limitler içerisinde ve oldukça da kısıtlayıcılar. Sizin yapmış olduğunuz yani sizin bize sunmuş olduğunuz araştırmalarda gördüğümüz kadarıyla buradakilerden daha fazlasında çimentonun azaltılması söz konusuydu. Yani bu konuda ne düşünüyorsunuz?
Yeah, I think I agree with you. I'm not an expert on how the standard should be set actually, but it seems like standards is quite strict restrictions on ways to limit CO2 emissions. So if you want to have a lower or products with lower CO2 content, carbon content, you probably have to look at the standards as well and see if it's possible to revise some of these standards. I think that would be very helpful for the cement industry. Just one comment also, you mentioned that in Norway we focus on carbon capture and storage and not carbon capture and utilization. But there are actually 2 factories that plan to be set up in Norway, where the plan is to use the captured carbon to produce what they call e-fuels, electro fuels, where actually they use CO2 and combine it with hydrogen from electrolysis of water to produce gasoline or diesel that can be used in transport. That is also a project we plan that's planned in Norway. So actually 2 factories are planning to do this in Norway. So that's one way of doing it. So I'm not sure if this is something you talk about in Turkey as well. Yeah.
Ya şu an için hani Türkiye'de baktığımızda bizler hani karbon yakalama konusunda çalışmamız gerektiğini biliyoruz. Bu konularda da halihazırda projelendirme yapan fabrikalarımız var. Ama dediğim gibi hani bizlerin direkt olarak hani karbon yakalamadıktan sonra onu kullanıma, yeniden kullanımı düşünmemiz gerekecek ilk etapta. Bizim planımızda da bu yer alacak. Gördüğüm kadarıyla başka bir soru yok ama son bir sorum da şeyle ilgili olacak. Ağaç kullanımı ile ilgili olarak hani alternatif olarak hani çimento ve betona alternatif olarak ağaç kullanımı. Şimdi bildiğimiz kadarıyla Avrupa'da Fransa özellikle bunun için hani ciddi anlamda bir lobi faaliyeti içerisinde. Ama şunu da biliyoruz hani bir ağacı kestiğiniz ve bunu kullandığınız zaman onun yerine yeni bir ağacın yani yetişebilmesi yaklaşık olarak 35-40 yıl. Hani bu konuda ne düşünüyorsunuz? Açıkçası bunu merak ediyorum.
Yes, you're totally right. So it's a kind of competition of land and also on the wood, because wood is important for storing CO2. You can store CO2 in constructions as well. Like if you use wooden buildings, that's also one way of storing it. But it takes also time to build to have the forest as it was again. But it is one way of storing CO2. I mean, you can, if you build a building based on wood, it may store CO2 maybe for 30, 50, 60, maybe up to 100 years, maybe even more. So it is actually one way of storing CO2 in buildings as well. So yeah, but the thing is that this is in a way a bit immature, because we don't really know how much, according to the literature, it's a bit hard to say exactly how much you can save on this, how much the potential is. Also in Northern Europe, I guess the potential is probably higher than in Southern Europe. And in addition to that, if you want high buildings, you still need steel constructions and maybe also cement constructions. So you can't really build a building based on wood totally if you want it to be very tall. So even if I mentioned that the tallest wooden building in the world is 85 meters, which is Norway, it also has a lot of steel constructions inside. So you need to do that. If it, otherwise, you wouldn't be able to build that high.
Tunç hocamın bir tane sorusu var sanıyorum. Kendisine el kaldırdı ama.
Yes, thank you very much for this great talk, Nora. Sorabilirim. Türkçe sorayım o zaman.
Olur hocam.
Şimdi bu karbon yakalamadaki maliyetlerin oldukça yüksek olduğunu görüyoruz. Sadece Norveç özelinde değil, birçok yerde böyle. Ve hesaplamalar da bu şekilde yapılmış durumda Snorre'nin çalışmasında. Fakat gelecekte bu maliyetlerde bir düşüş bekleyebilir miyiz? Hani bu iş yani yakalamaya başladıktan sonra işte bu öğrenmeyle birlikte ve de belki teknolojik gelişmeyle birlikte bu maliyetlerde bir düşüş beklenebilir mi? Ve bu hani belki kararları da değiştirecek nitelikte düşüşlerde olabilir mi diye merak ediyorum.
Yes, this is right. So we will probably expect falling costs in the future. Another thing is that the price of carbon permits in Europe has been very high. The EU ETS price has been very high. It's been up to something like €100 per ton of CO2 recently. At the moment, it's about €80 per ton of CO2. So if the carbon price is going to be that high, it may be more economically beneficial to invest in CCS in the future. Another thing is that there are several imperfections in the market for carbon capture and storage. One is the economics of scale, meaning that you need to store and capture a quite high amount if it's going to be beneficial, because you have quite high upfront investments. There is some kind of monopoly in the storage side, in storage, and it could be a monopoly or at least duopoly when it comes to transportation, which means that the costs are also higher due to this market power. And there's several actually other, maybe also other imperfections that actually makes it quite hard to do this. So I think this requires some kind of policy instruments from the government to be beneficial. But I think the good news is that ETS price, the carbon permit price, is very high, and it's probably going to be quite high in the future. It means that the CCS can actually be economically beneficial for industry in the future.
Teşekkürler. Serkan Bey'in bir sorusu var. Çimento bacasına direkt havadan yakalama neden uygulamıyoruz? Bunu kısıtlayan nedir? Belki buna Sayın Kıvendorp cevap veremeyebilir ama kendi uzmanlık alanı değil. Ben literatür bilgisiyle kendisine cevap vermeye çalışayım Serkan Bey. Yani şöyle bir durum var. Şu anki yakalama sistemlerinde genelde membran ya da bazı solventler kullanılıyor ve bu solventlerde karbon yakalama eğilimi olan solventler, yani çözücüler ya da membran sistemleri. Siz de biliyorsunuz ki çimento bacasında kömür yanıp emisyonla birlikte SOx'lar, NOx'lar ve karbon monoksit ve karbondioksit olarak atılım gerçekleşiyor. Bunların hepsini siz direkt olarak sisteme beslerseniz membran sistemin ya da çözücünün rejenerasyon ömrünü ya da kullanım ömrünü azaltıyorsunuz. Bu yüzden de sistemlere genelde ilk önce SOx'lar ve NOx'lar ayrıştırılarak membranlara karbondioksitin direkt iletilmesi isteniyor. Bir tanesi bu olabilir. Bir diğeri de bacadan attığımız gazın belli bir sıcaklığı var. Bazı membranlar karbon yakalama için kullanılabilmesi adına sıcaklığın 60 derecenin altına indirilmesi gerekiyor. Ondan sonrasında membran sistemi ya da çözücüye gönderebiliyorsunuz gazı. Belki direkt havadan yakalama şu an buna cevaz vermiyor olabilir. Ama şunu biliyoruz, literatürde direkt havadan yakalama çalışmaları günden güne artmakta. Sanıyorum gelecekte bunlar daha çok karşımıza çıkacak diye düşünüyorum. Bilmiyorum, cevap olmuştur umarım Serkan Bey'in sorusuna bu. Şimdi bakıyorum başka soru ya da yorum yok bu konuyla ilgili. Kıvendorp, son söylemek istediğiniz bir sözünüz var mıdır? Yoksa bugünkü webinarımızı ben kapatacağım.
I just want to say thank you again for inviting me. I think it's been an interesting discussion, and I hope that you actually benefited from my presentation as well. So thank you.
Biz çok teşekkür ediyoruz. Çok faydalı oldu. Norveç tarafında yapılan uygulamalar ya da bu taraftaki literatür çalışmalarının ne olduğunu bizler de görmüş olduk. Kendi üzerimize düşen ödevler nedir? Bildiğimiz vardı, onun üzerine eklememiz gereken şeyler olduğunu gördük. O yüzden biz de çok teşekkür ediyoruz. Bugünkü davetimizi kabul ettiniz ve bizi kırmayarak buraya katılım sağladınız. Ben değerli katılımcılara da bizimle birlikte oldukları için çok teşekkür ediyorum. Herkese iyi günler diliyorum.
Thank you.
Pınar Hanım, Aylin Hanım, sizlere de çok teşekkür ederiz. Bu arada sizleri unuttum zannetmeyin lütfen. Desteğiniz için çok teşekkür ederiz. Çok sağ olun. Görüşmek üzere, iyi günler.
Görüşmek
Sağ
üzere.
olun.
Kendinize iyi bakın.